Thank you. So, hi everyone. This session of the book club, we're going to look at chapter 6 from the Statistical Learning book, which basically covers linear model selection and regularization. So basically just looking at ways to improve our regression models. So we all know and familiar with the standard linear model, but it does have some limitations. So we're looking at better prediction accuracy, more specifically towards the testing cases, and also trying to improve model interpretability. So there's a few different ways of doing it. So one of them is subset selection, and then we might look at shrinkage and regularization. I don't think we'll have time to look into dimension reduction, but we'll probably look into that the next session. So if we look at the standard linear model, so the problem with the standard linear model is that we encounter prediction accuracy issues when there are many observations with few predictors. So in this case, least square works really well, but that's because you've got plenty of data to estimate each coefficient, and the variance will be low. So using an example would be if you want to predict house prices and you've got 1,000 houses as your data observation points based on just 3 features. But when it comes to real world applications, it's probably not going to be the most practical usage of a model. And then when you have n is somewhat equivalent to p, so you have similar number of observations and predictors, it can lead to high variance in coefficient estimates, because if you've got any tiny changes in your training data, it can cause a lot of changes in the estimated coefficients. So the sensitivity increases and you also risk overfitting. So that's not necessarily as sort of stable and predictable of a model as you want. But when you have a lot more predictors than observations, there's a lot more solutions with perfect training fit, but you have very poor test performance. So what's happening is that the model is essentially perfectly fitted the training data, but when it comes to using it on a testing set, the model performs really badly. So if we just look at this type of illustration.
Sorry, can I pop in for a second?
Yeah.
What were you saying about prediction accuracy and the number of data points being greater than the number of predictors? Sorry.
Oh, when n is greater than p.
Yeah. So
Yeah.
you said if we have 1,000 prices for houses or whatever, and we have 3 predictors. Did you say that is good or bad?
That is probably better than when you have when it's the other way around.
Yeah.
But again, you're just using a few predictors, so sort of like small changes in the data can cause big swings in like coefficients. But then, for example, when like n is much greater than p, you're very much like limiting your ability to predict accurately or well when it comes to like testing cases. So you're essentially like limiting yourself in terms of like predictability. When you, let's say like you want to like predict house prices, but in the real world, house prices is based on much more predictive factors than like 3 predictors.
Okay. That's not exactly what I interpreted from that chapter. I thought it was saying that if n is far greater than p, you're going to get like quite a good general model, which will perform well in the test set.
Cases, it's probably the best case in terms of the standard linear model.
Okay. Yeah, just if you have like lots of observations and I guess fewer predictors, you're going to create like a good general model that will kind of have low variance and should perform similarly well, I guess, on the test set. Whereas if you have a high number of predictors, you're going to tend to like fit more to the test set specifically, and you might have higher variability then when you get to
Yeah, so in terms of those three situations, where you want to be is N is far greater than P versus
okay,
two scenarios, essentially.
Okay.
So yeah, and then the problem illustrated, so you can see this is a fitted line that essentially the line of best fit fits around the data much better. And then the case where the observations equals the number of predictors, it's deceivingly sort of perfectly fitted, but that's very much just a deception. That's not necessarily the case because you have very limited observation. So it's making a very good approximation of the relationship. But again, it's just a deceitful line of best fit. Again, when you do it on the testing set, it's not, the model's not going to predict very well versus a scenario such as this. So that is a visual illustration of that. So if we move on to some subset selection methods. So BSS, so best subset selection, is a method to fit separate least squares regression for each possible combination of P predictors. So we basically fit all predictive variables models that contain exactly one predictor. So how it works is like you essentially start off with one predictor, then two predictors, and then you keep going until all the predictors are included in the best subset selection. So first you start off with the null model with no predictors. So that's essentially just the intercept, and that's just the baseline model. Hardly anyone would sort of use this in the real world. And then for the next step, you increase each predictor individually, and then you try each possible pair of predictors, and then you try each possible triplet predictors, and so on and so forth. And then it's very much based on whichever model has the lowest residual sum of squares. So for each subset, we identify just one champion model, and then we choose the overall best model. So the null model plus one best model for each size 1 through P. And we can use different criteria like cross-validation error. I think this was touched roughly in the previous chapter. I think Aoife, you covered that. And we also have MalloCP, BIC, adjusted R squared. We'll go into MalloCP, etc., more so in a bit. But essentially, the computational challenge is that the total number of models we need to fit is the sum from K equals to 0. So P choose K, which equals to 2 to the power of P. So as examples, so when P equals 10 predictors, 2 to the 10th power equals 1024 models, P equals 20 predictors, 2 to the 20th equals more than 1 million models. And then before you know it, if you've had loads of predictors, you are computationally trying to reevaluate on over 1 trillion models. So it's incredibly computationally heavy. And so when you have a model where you need a lot of predictors, it's not necessarily realistic feasible to use best subset selection. And we need a criteria to select the best one, but we can't always rely on RSS or R squared because they typically have a bias towards the most complex model. So that's where these other evaluation metrics come in. So MalloCP is for a fitted least squares model with D predictors. So it's CP 1 over n times, so it's RSS plus 2D sigma squared, where essentially sigma squared is estimated from the full model with all predictors. Essentially, the MalloCP adds a penalty of 2D sigma squared to the training RSS to adjust for the fact that training error underestimates test error. And then the penalty increases with more predictors. So you can't just keep adding predictors and predictors into your model without malloc punishing you for it, because you're making your model too overcomplicated. So we would choose the model with the lowest malloc value in this case. Another way to evaluate your model would be AIC, which is possibly pronounced as Akaike information criterion, but I could be wrong. It's proportional to malloc. So it's essentially, the formula is 1 over n times the RSS plus 2D sigma squared. And it's a little bit more generalized, in which case that you can apply it to more models beyond linear regression, particularly those that fit using maximum likelihood. And then the next one, you've got Bayesian information criterion.
Sorry, I'm going to jump in again, if that's okay.
Yeah.
The formula for it, and sorry, I'm just looking at it, it's the same as in the book as well, and I have done no external reading, so I don't know the answer to this. The formula for CP and AIC there is the exact same. Do you know what the difference between the two of them is?
I don't know. I think I just basically Googled it. Let me just have a look. Is it the AIC?
Yeah, the just formulas you have there, and the formulas in the book are the same. Yeah, okay. So it says in the book, sorry, so for simplicity, they've omitted irrelevant constants for AIC. So for least squares models, CP and AIC are proportional to each other. Okay, so yeah, they're kind of saying they're the same. I don't really know the difference between them is.
Yeah, I mean,
have like a more complicated error term than just you know, I mean, at least just looking at the note, it says for linear model Gaussian errors. So maybe if you modeled the error also, then maybe they'll be different. But otherwise.
Okay. I'm gonna do some Googling while you keep chatting, Cheryn.
yes.
Yeah. Sorry, guys, just to jump in, like, obviously, like, please don't have to answer this now, Cheryn. I think just as in, like, maybe it'll be something we can look as a group, in terms of activities or questions, but it would be interesting to see, like, the implications of non-Gaussian error distributions on the effectiveness of the AIC formula. Just, you'll be curious. I'm curious. I'd be curious to see that.
Yep.
But, like, again, not something you have to answer now, just more for the group.
Yeah, can make a note. I mean, does anyone know?
Yeah, if anyone knows, please jump in.
I feel like Sandrine might know, but she's not here. So, yeah. I found a variation of the AIC. It's like 1 over n lambda squared RSS plus 2d lambda squared again. So this is just from like Googling, but I'm also seeing loads of like different variations of the AIC. So I think maybe it depends whether you're employing RSS in your computation of AIC, but we can come back to that. My screen's good. Okay, so next is Bayesian information criterion. So this is similar to malloc. So it's equals 1 over n times RSS plus log of n times d times sigma squared. So it essentially prefers smaller models than malloc or AIC. So this is just in reference to the credit data set that where it showed in the book, BIC selected a 4-variable model, whereas CP chose a 6-variable model. So that's something to bear in mind. Bayesian would have a larger punishment for complex models versus malloc or AIC. So that's something to just bear in mind. And then you have the adjusted R squared. So it's 1 minus RSS over n minus d minus 1 over TSS divided by n minus 1. So TSS is the total sum squared. So while the regular R squared always increases with more variables. So that's just a little illustration of which model is optimum based on these different criterion. So as you can see, the RSS usually decreases with more variables, but then it flattens out. And then the adjusted R-squares peaks around 10, 11 variables. And then Mallow CP suggests something similar, around, well, adjusted R-square probably looks like it prefers 11, whereas Mallow CP looks like it's preferring 10. And then you've got the BIC that's looking like it prefers about 6. So that's something to bear in mind, and just like a quick little like illustration of the different metrics. And what have I said? Well, we can't use the RSS by itself as it tends to favor the most complex model. I think I mentioned this earlier. And then Mallow CP estimates the prediction error, again, marking around 10. All in all, the best subset selection can't be applied with a very large amount of predictors, as we mentioned before, because it's computationally incredibly heavy. You can't be evaluating over 1 trillion models at any one time in terms of choosing the best model to work with. So the larger your P, the higher chance of finding models that look good. So we can look at another method, which is stepwise. So first is forward stepwise. So instead of considering possibly over 1 trillion model selection of all predictors, forward stepwise considers a much smaller set of models beginning with no predictors, and then it adds predictors one at a time until all are in the model. So the variable that actually gives the greatest marginal or additional improvement is then actually added to the model. So this is just a simple table that I just extracted from the textbook. So what the book did was illustrate how forward stepwise would work on the credit data set. So if we look at when we have one variable, best subset and forward stepwise similar, same as 2 variables, same as 3. But then at the 4th variable is when there is a difference. So best subset is essentially trying to iterate across all models without considering the impact of the improvement of the fit that's actually added to the model, whereas forward stepwise is. So that's where you find a discrepancy, where forward stepwise would choose rating and then best subset would choose cards, because it just is the next predictor to evaluate in terms of the 2 to the power of P possibilities. So that's forward stepwise. Backward stepwise essentially is similar, but it works in reverse. So you start with all predictors and then it removes the least useful one with each step. So one limitation is that it actually needs more observations than predictors to get started. So again, N needs to be much greater than P. Otherwise, forward stepwise would work even when P is greater than N. So that's something to bear in mind when choosing the different stepwise selections. And then, so why you need to choose the best model, we can either make an adjustment to the training error to account for bias due to overfitting, or directly estimate the test error using validation set or cross-validation approaches. So these are just the different ways that you can try. I think a lot of people would prefer to use validation or cross-validation approaches, but I don't know, has anyone in real life used any of these sort of AIC, BIC methods?
I certainly have. When I was in university, I've used those as opposed to validation sets. But yeah, in real life, I think always a validation set.
Is that just preference, or do you think like validation sets are just more reliable?
Yeah, well, yeah, because like AIC, BIC are estimates of what you're finding out with the validation set, like when you have a validation or test set or whatever you're calling it. That's what AIC is attempting to estimate. So yeah, I would say having enough data for a validation set would be...
Yeah, I can't imagine anyone, like in real world anyway, in terms of when you're working an actual job, and then let's say you're trying to choose the best model, and before choosing and push the model into production, I don't know if anyone would rely on estimating the test error versus just extracting the actual test error.
I guess it depends how much data you have. Maybe you don't have enough data for like a validation set, or maybe if whatever you're modeling isn't particularly critical, maybe you don't have enough data, maybe push to production. I don't know if anyone else has any experience.
I'm gonna take that silence as a no. Okay, cool. We're all friends of validation sets, and yeah, cool. All right, so shrinkage methods next. So the subset selection methods uses least squares to fit a linear model, and it contains a subset of the predictors, but we can also fit a model containing all predictors that constrains or regularizes the coefficient estimates and essentially shrink them towards zero. So this significantly reduces their variance. And so we can look at ridge regression and lasso. So we're going to look at ridge regression. So ridge regression essentially adds a penalty term proportional to the sum of squared coefficients. So this shrinks the coefficients towards zero, which significantly reduces their variance. So the parameter lambda controls how much we penalize large coefficients. So when lambda equals zero, we get regular least squares. And as lambda increases, coefficients shrink towards zero. So this actually just creates a trade-off. As we constrain flexibility, we reduce variance, but then we also increase bias. So it works well when least squares estimates have a really high variance, especially when you have a high number of predictors that's very close to or greater than n, which is your number of observations. But essentially what ridge regression is trying to do is try and get your coefficient essentially as low of a variance as possible without necessarily compromising too much bias as a trade-off. So when can we use ridge regression? So when least squares estimates have a high variance, i.e. when P is almost as large as n, or when the predictors is greater than n, is actually a scenario where it would be quite suitable to use ridge regression. And that is it. I didn't think we would get so far, but yeah, I was trying to save some stuff. So we're going to look at lasso and PCA next session.
Can you discuss a little bit more what you mean by bias? So you're saying if you increase lambda, you're going to shrink your predictor coefficients. And you said that will increase bias?
Yes. So
what?
I suppose bias is more so in the sense where it favors certain coefficients, beta coefficients numerics more than others, but that doesn't necessarily mean it's reflective in terms of its absolute final most accurate like coefficients in terms of your predictors. So that I think that's more so what I mean when you decrease your variance. You try to, again, what ridge regression is doing is you're essentially trying to shrink the coefficients as much as possible. And because of this, it's very much leading to this sort of skewed belief that the coefficients should be as low as ridge regression is suggesting them to be, but that's not necessarily the case, again, when it comes to cross-validating and estimating the true test performance of the model.
So I'm not super familiar with shrinkage methods or ridge regression, so my understanding of this could be wrong. But my understanding of why you'd use ridge regression is you want to prevent overfitting. So if you have loads of predictors, and they all have like these significant coefficients, you're going to tend to overfit to the training data. So you might use ridge regression, so you reduce the size of some of these parameters, or the coefficients of the predictor parameters. And that should, in theory, the whole reason for doing it, I think, is so that there's less bias in the model, so that your output model is going to generalize better. So it's to prevent overfitting and to prevent bias towards the training data and make your model more generalizable, I think. So I would think that it would reduce bias if you were increasing lambda. I'm not 100% sure how you choose an optimal lambda or what happens if you start throwing lambda very high. But
I was having a hard time wrapping my head around this also, and like I think was trying to kind of distinguish in my mind between like a biased coefficient and like a biased model. And maybe one's a subset of the other, but like it's easy to see how ridge regression could lead to biased coefficients because basically you're like taking the risk that you're going to leave out like a variable basically that is actually important. And so then maybe that variable becomes like a confounder. And then so your estimates for individual coefficients are going to be inaccurate. But yeah, it was harder for me to imagine. And I think you were kind of talking about this at the beginning as well, is like if you don't have enough coefficients, are your predictions going to be worse? And I don't know, that was harder for me to answer. Maybe the answer to that isn't as general. Yeah, it's hard to say that
I found this like illustration. I don't know if that helps anyone.
Oh.
So it seems as if it's, inversed between variance and bias.
So,
and then all whilst trying to get minimum total error.
So as your model complexity goes up, your variance goes up. And your bias goes down. And so what is bias? What that's model bias, not coefficient bias then, is it?
I think so. It's efficiency parameter estimation problems.
Okay, maybe I need to do some reading on what bias is here.
Yeah, I mean, I think they both can cause poor predictive performance, but just like, maybe there's kind of a sweet spot where you're kind of minimizing them and you're getting the best predictions. But if you have too much of either, then you're in a bad situation. Although
But I wonder,
I guess, on the data.
unless it extends to both, whether it's the model as well as the coefficients themselves. Possibly. This is just a stab in the dark.
Can you talk to how it actually minimizes or shrinks the coefficients? Like what's it actually doing to shrink the coefficients?
The shrinkage method.
Yeah, like in ridge regression, like it's not, I assume it's not shrinking all of the coefficients by the same amount, is it? And maybe I could figure this out if I sat down with this.
Is it
formula in front of me, but I haven't. Like I'm assuming that it's shrinking what it's deeming to be less important coefficients towards zero. And maybe it's shrinking all of them, but I'm assuming it's not like
I'm assuming it is shrinking
all of them. All proportionally, it's not going to change the model really. Or it'll change it, but
Because if we increase lambda, then the sum of beta squared is essentially after balanced out. In which case I would assume that it is shrinking all the coefficients at the same time.
yeah, but is it shrinking them by the same amount or the same proportion, or how is it deciding by how much to shrink them?
I want to say yes, just by looking at the formula, lambda is just applied.
Yeah, my intuition is that like basically the closer to zero you get, the more like you're more likely to get shrunk. But I'm having a hard time seeing that in the formula. I might need to look at it more closely
I
also.
remember ages ago, I watched a YouTube video on ridge regression and lasso regression. That was really good, but I forget everything it said.
Does it shrink it all at the same time? Literally just googling it out.
Aoife, if you remember that video at some point, if it strikes you, could you send it, please?
Years ago, Sophie, I have no idea.
If it comes to you in a dream, you know, here's hoping.
Oh, IBM says no, it doesn't.
Yeah, I don't think it would make sense if it did shrink them all the same amount. So
they're shrunk in proportion to their initial size, and then as lambda increase, high value coefficients shrink at a greater rate than low value coefficients. So that makes more sense.
okay.
But it's hard to tell based on this formula. Because this is the shrinkage penalty. Okay, so the coefficient of beta squared, so the larger the original beta value.
Is beta is the coefficient, is it?
Yeah,
Okay.
so the larger the original beta value, the greater the shrinkage penalty is.
Okay.
Oh yeah, I literally said that penalty is small, coefficients close to zero. Yeah.
Okay.
Yeah, although it's hard, I don't know, it's hard to see. I guess the way you have to minimize that quantity, I guess, is like you have in particular are values that minimize this. And so I don't know. I guess we'd have to like work through that. Maybe someone's done that on the internet. Because yeah, I think from that it's hard. I don't know. I don't see how there's um any difference in which coefficients get, or the degree to which different coefficients get shrunk. But yeah, it doesn't make sense to shrink them all the same. Yeah.
I'll put my hand up. I haven't gone through the lab, so I don't know if there was like a demonstration in one of the lab's questions actually demonstrating the ridge regression penalty on specific given coefficients.
I haven't done that.
Yeah, I'm actually just looking at the figure 6.4. So on the x-axis, it has the ridge regression coefficients, and the y-axis is the standardized coefficients. Is that, I don't know, is that supposed to be the value of the coefficients, I'm guessing, or the initial value? And it looks like actually rating, for example, the blue dotted line increases before it starts decreasing, with an increasing ridge regression coefficient. I'm gonna have to go through this.
Yeah, there's a lot.
Am I imagining that? Am I like interpreting that plot wrong? I don't know. Has anyone else got it in front of them? Anyway, okay, will I hit stop in the
Oh yeah, we're just discussing at this point, please.